Well, welcome back. This is Unit 3.2, and this is Periodic Table and Trends. This is going to be addressed in Chapter 6 of your textbook. All right, so the first thing that we're going to talk about is the periodic law. And this is a law that says that at certain intervals, the properties, chemical properties of the elements on the periodic table start repeating. And so as far back as the 1800s, scientists were looking at the chemicals and they noticed that certain chemicals have certain chemical properties. For example, Johann Dobenheimer noticed similarities in several groups of these elements, such as chlorine, bromine, and iodine, which are three elements that are in group 17. And he noticed this with other elements, and he started calling these triads because these three elements would have similar properties. But way back before this, even in ancient times, people had elements that they saw had similar properties, such as the precious metals like gold, silver, bronze, which is really a mixture of elements. In 1857, an English chemist, William Odling, proposed that the elements could be divided into groups based on their chemical and physical properties. And many of these groups actually resembled the vertical columns that we have in the periodic table today. In 1862, a geologist, a French geologist, Jean Courtois, arranged the elements by increasing atomic mass, and he noted that elements with similar properties seem to occur at regular intervals as well. And he devised a spiraling graph. It's really the periodic table that was like in a circular graph. But his paper didn't get much attention because it was really complicated, and he left out major parts of the paper, paragraphs of the paper. And he approached it from a geologist's point of view because he was a geologist. So he didn't get very much attention for his periodic law proposal. But in 1864, another chemist, John Newlands, noticed that similar properties seem to repeat every 18th element, in much the same way that the notes on a musical scale repeat every 8th element. There's that magic number again, 8. Is that a coincidence? I don't know. And he called this the law of octaves because he was comparing it to musical notes. But the most successful organization of the periodic table came from actually two scientists, a German scientist, Julius Meyer, and a Russian scientist, Dmitry Mendeleev. And the chemical community ultimately awarded the notoriety to Mendeleev for three reasons. And this is really important because Mendeleev's paper was submitted almost a year earlier than Meyer. They were working independently. They were not working together. So they came up with this at the almost exact same time. But Dmitry Mendeleev was just a little bit ahead of Meyer. Also, Mendeleev concentrated on the chemical properties of the elements where Meyer focused on the physical properties. And for the third and probably the most important reason, Mendeleev chose to leave blank spaces on his table where he predicted elements would be discovered. So if we look at this right here we see zinc, right? Well, here you see this blank. So he proposed that there would be an element discovered there with an atomic mass of 68 that hasn't been discovered yet. And he also had one right beside it that he left blank with an atomic mass of 72 that would be discovered, but we didn't know about it yet. So this really corresponds to germanium and gallium, the two elements, germanium and gallium, that he didn't know about, that weren't discovered yet, and ended up that he was correct. that they were discovered, and it did have atomic masses that corresponded to this. So Dmitry Mendeleev is called the father of the periodic table because of his proposal. So all this comes down to the periodic law. And I know we use the terms law and theory sometimes interchangeably, but I want to make sure that I clear up the difference between a theory and a law. A law explains that something exists, just that something is there. So when he said that we have this periodic law, he was saying that it exists. It's a thing where every 18th element, the chemical properties start repeating. As opposed to a theory attempts to explain why the relationships or phenomenon exists. So he wasn't explaining why. He was just saying that it exists. The periodic law exists. So that's a difference between a law and a theory. All right, and this was back in 62, I believe, 1869, where all of this, right there it is, where Dmitry Mendeleev proposed this. And this was pretty much the accepted periodic table for about 50-ish years, up until 1913. And then data that's being gathered by a British chemist named Henry Moseley, who was doing his work in X-ray spectra with crystals, led to the discovery of isotopes, which resulted. Okay, so remember, isotopes have to do with the neutrons that are in the nucleus of elements. So this resulted in him discovering the atomic number of elements, and thus resulted in the periodic table being rearranged just slightly according to atomic numbers instead of atomic mass. So let's go back. And Dmitry Mendeleev arranged his table according to atomic mass. Okay. And then because of Mendeleev's work in X-ray spectra, it was rearranged according to atomic number. And so Moseley's version of the periodic table is one that we still use today, with the addition of some new elements that have been discovered, mainly these right here. So if you'll look at the periodic table in the classroom, then our periodic table ends, I think, with 113 or 112, but some more elements right here are being added and discovered. All right, so there's a few things that I want to point out on the periodic table before we go any further, and we're going to do more of this in class, but mainly right here, just draw a rough sketch of the periodic table and label this. Across the top here, you see these numbers. Okay, these represent group numbers. So these are the groups of chemicals that have similar chemical properties. And remember, chemical properties refer to the way that they react with other elements. So beryllium, magnesium, calcium, strontium, and barium all have similar chemical properties. They react in a similar way with other elements or compounds. Okay, so 1 through 18, these are called groups. These are the groups of the periodic table. Now, they used to be called families. Families is like an old school name, but a more appropriate and accurate and modern terminology is groups. These are groups. Okay, now down the periodic table, you'll see that these numbers here refer to the periods. Okay, so periodically, these properties start repeating. And so they repeat, and these are called periods. These rows, these principal energy levels are called periods. All right. Also on the periodic table, we have here representative elements. These first two groups here, and then 13 through 18 are also called representative elements because they mainly represent the main characteristics of the periodic table. They pretty much adhere to, the rules as far as electron configuration and bonding. But the transition elements here, 3 through 12, these right here, the D block orbitals, these are called the transition elements. Okay, and they're mostly or transition metals, you may hear it referred to. Okay, so these are some introductory, I would say, groups or divisions or areas of the periodic table that we're going to ultimately need to know. All right, so talking about trends now, the first trend that we're going to talk about is called atomic size or atomic radius. And there's two factors that are influencing atomic radius. Number one, the number of principal energy levels that are present in the element. So hydrogen, okay, so I'm going to write here the periods or the principal energy levels. Now remember, when we get to the end of a period, it starts over with the S block, right? So we get 6P1, P2, P3, P4, P5, P6. We're going to go down to the next line, and it's going to be 4S1. Well, what's happening here is we're adding another outer orbital. So think about these as shells. So this has one shell, okay? And then all of these elements on period 2 have one plus another one, so it's two shells, okay? And then when we add this one, we get down to sodium, it's got three shells, so it's got this one, and then we add another one. So if we're adding layers, it's kind of like a gobstopper. When you're adding layers, the gobstopper gets larger and larger and larger. So that's what's happening here. As you're adding these principal energy levels that electrons exist in, the size or the radius of the element gets bigger and bigger. So you see, as we go down the periodic table, we're adding shells, and so the radius of these gets larger and larger. Okay, so that's the first factor. The second factor is the amount of effective nuclear charge, and that's a really important word there. I underlined it and bolded it because it's a very important term that you're going to hear over and over. The effective nuclear charge that's felt or seen by the outer electrons as the number of protons increases in the nucleus. These outer electrons feel an increase in the pull of this outer shell. So it's easier to see if we start down here on 4. So the protons are pulling on the electrons because the protons are positive, the electrons are negative. So as we go across the periodic table, remember, we're adding a proton. And as we add protons, there's more and more positive charge, effective nuclear charge that's in the nucleus that's going to be pulling on these electrons, but we're not adding any more electron shells. This is only on the 4th energy level. So the distance that these electrons are from the nucleus depends on how much pull the nucleus is pulling on them. So as we go across, we're adding more and more protons that are pulling on the electrons. So in return, that pulls the shell closer and closer and closer. So you see the trend here as we go across, as we're adding protons and it's pulling on those outer shell electrons, it's pulling more and more and more till we finally get over here. And then when we add this other shell, it gets big again. And as you go across, it's pulling closer and closer and closer. Okay. And so we see that here in this graph. So if this is on the x-axis, the radius, and this here is the atomic number, we're going to see that helium has the smallest radius right here. Okay. But now we're going to add a shell. So that's going to make lithium large. Okay, and so as we travel across, as we add protons to the nucleus, it pulls that shell in closer and closer and closer till you get to neon right here. So neon is, again, the radius is small, but it's not as small as helium. Okay, and then so we start with a new period. It adds a new shell, so the radius pops back up. So neon pops back up larger. And then again, as we go across and add protons, it gets smaller and smaller. And then potassium, large, smaller and smaller. Okay, and here's the d orbital. Okay, so you see that little hump there? These are the d orbitals right in through here. The transition metals. Okay, and then you get to krypton, and boom, back up to rubidium, it gets large again. So here you see all of the noble gases, okay? Noble gases right here. And here are all of the group 1 elements that have the large radiuses. Okay, so if you remember this alliteration, remember alliteration means that the letters are repeating, large, left, alliteration, big bottom, then you can remember the trends on the periodic table. So the larger radius elements are on the left, and the bigger radius elements are towards the bottom. So the trend looks like this: large left, big bottom. So the largest radius is going to be down here in this area. And for this periodic table, they only have 6 of the periods. They didn't add the 7th period. Okay, so for this drawing that they have, cesium is the largest. And of course, helium is the smallest radius. All right. And so this leads us to the other 2 trends that we need to know: ionization energy and electronegativity. And these really refer to, we're going to talk about these more when we start talking about bonding and the way that elements bond with each other. Ionization energy is used a lot when we talk about ionic bonding. Okay, so ionization, ionic bonding. Okay, and then electronegativity we talk a lot about when we talk about covalent bonding and about, I would say electronegativity is probably one of the most important trends, because we talk about it a lot in covalent bonding. We also talk about it a lot when we talk about the shapes of molecules and the way that 2 molecules interact with each other. So we'll be talking about electronegativity a lot. But first, let's define these. All right, so ionization energy is the minimum amount of energy that's required to remove an electron from a gaseous atom or ion. So we're removing electrons. And remember, if you remove electrons, it's called an ion. Removing electrons is called an ion. Specifically, removing an electron is called not an anion. Removing electrons would result in a cation. Okay? But adding electrons is called an anion. Okay? But removing electrons creates a cation because it makes it positive. And remember, cats have pause. All right, so ionization energy tells us how strongly an atom holds on to its outermost electrons. And remember, the outermost electrons are called what kind of electrons? Valence electrons. Okay, so as atomic size decreases, ionization energy should increase. And as the atomic size increases, ionization energy should decrease. So let's look at that. So here, how strongly it holds on to its electrons. So if we look at helium, helium is very small. So the distance that the electrons are from the nucleus, which is holding on to the electrons, is very, very small. That distance is small. So this ionization energy, in order to get an electron off of there, it's going to take a lot of energy because the electrons are so close to the nucleus. However, let's look at cesium. So there's the nucleus. Look how far relatively these electrons are from the nucleus. So cesium, the energy is going to be really low. It's going to be relatively easy to pull an electron off cesium. Well, when we pull that electron off cesium, then it has the same amount of electrons as xenon. Okay? So these are called isoelectric, elements that have the same number of electrons. So cesium plus 1 is isoelectric to xenon. So it looks like xenon. It has the same number of electrons. Now look at xenon. Okay, so look how close these electrons are to the nucleus. So it's really, really, really hard to pull another electron off. So after you take this first electron off cesium, then it becomes really hard to take off the second electron because of the distance the electrons are from the nucleus. All right? So that's ionization energy. Now, electronegativity is the ability of a bonded atom to attract shared electrons to itself. So atoms with a high electronegativity tend to pull bonded electrons close to their nucleus. So they pull electrons. So smaller atoms feel this nuclear charge in their outer shell electrons more than larger atoms. Okay, so if we go back again, we're talking about the ability to attract electrons to itself. So all of these right here have zero electronegativity because their outer shell is already filled with 8 electrons. They're called the noble gases. So we're not going to talk about these because they don't want to attract electrons to them. But fluorine in its outer shell has 7 electrons. And if it had 8 electrons, then it would be isoelectric to the noble gases, and it would have a filled orbital and be very stable. So fluorine here, 1, 2, 3, 4, 5, 6, 7. But these 7 electrons really wants to attract one more electron to itself. Okay? And if it does, it's going to have a stable orbital. And look how close the nucleus is to these outer shell electrons. See how close that is? So fluorine really, these electrons really have a great pull. Fluorine really pulls strongly to pull electrons off other elements. As opposed to cesium, right here, right there, has only 1 electron in its outer shell. And so it wants to pull 7 more electrons, okay? 7 more electrons. And it's really hard. It's really easy to find 1 electron, especially with the nucleus this close. But look at cesium. It needs to pull 7 electrons. And look how far away the nucleus is to the outer shell. So this pull is going to be really low. Okay, so the electronegativity of cesium is really low, where the electronegativity of fluorine is really high. Okay, so the trend is electronegativity increases this way, and it increases this way. Okay, so you can think of electronegativity and ionization energy being opposite of the atomic size or atomic radius. Okay, so you really need to know why this is happening. Okay, and we'll talk more about this in as we go through the other sections and other units in chemistry. So that is it for this video. Make sure you slap that like button right across the face, and make sure that you give me a like and a subscribe, and leave a comment down below.